Hi, I wanted to give a quick illustration of why 3x plus 1 sequences do not loop, except for that well-known trivial loop, 1, 4, 2, 1. And the reason is to do with common differences. So most people think of a loop as being a sequence of numbers that repeat periodically, and by repeating the same number, one number, all the other numbers that follow must be repeating too. Well, that's one way to look at it, but it's actually the result of a loop, not the cause of the loop. The cause of a loop is, in fact, any sequence of numbers whose common differences sum to 0. And in this definition, it actually doesn't matter at all what order the numbers are in as long as they sum to 0. So the way to understand this is to look at a counterexample. Counterexamples are easy to find and very instructive. By a counterexample, in the way I'm using that idea, instead of using 3x plus 1 with 1 as the addend, I'm using a greater number here, 3x plus 17. And I'm just running the number n equals 27 through this variant of the function, and we see right away that we get a complex loop. And I've graphed the loop, and essentially I'm showing the same loop twice. The loop ends effectively on the number before the repeating number, and then it's just starting again, so the repeating number is the first number in the loop. Here I show exactly why there is a loop for the foregoing example, and we see that starting on 27, when we hit 11, we enter the loop, and we know this is the loop, of course, because 11 repeats again. Now, if we look at the common differences between these numbers, so 11 minus 25 is minus 14, 25 minus 23 is 2, 23 minus 43 is minus 20. Those are the common differences. If we sum the common differences, we get a big fat 0. Okay, and that's why it is a loop. That is the long and the short of it. There is no other reason. It wouldn't matter what order these numbers were in, you would still get a loop because the common difference is sum to 0. It wouldn't matter if the loop was, very short. I'm not sure if 2 would work, but certainly 3 or 4 digits, as long as they cancel themselves out. Here we have the even-odd sequence for the same counterexample, 3n plus 17, where the input number is 27. And obviously the sequence is unfamiliar if you're comparing it to 3x plus 1. So, for example, 41 times 3 is 123 plus 17, which makes it 140. Now 140 is the first number in the loop, and we see it repeating over here. So technically the last number in the loop is 280, and we see here this principle that there are two ways for which an even number, two inputs for an even number. And so we have one odd input 41 and one even input 280, something that seems to confound mathematicians. And so we see equivalently that there'll always be a loop for the even-odd sequence as there is for the odd sequence. Well, how do you account for this phenomenon? There must be a rational explanation, and indeed there is. It's to do with the symmetry of common differences. And it turns out that any number, let's say greater than 3n plus 5, that's when I say number, I'm saying the addend, makes it possible for there to be a symmetric common difference on either side of the equilibrium point, and I'm just defining the equilibrium point as the addend. So you will find in 3x plus 17 that you have, and this is here I'm just lining up the natural numbers, the counting numbers, and I'm showing their outputs according to my function, my order-only function, which produces superset numbers as well. So some of these numbers may not be familiar, but we do see this where input 11 is output 25, and input 13 is output minus 14. So that's 14 and minus 14, which cancel each other out. And we also see a pair on the other side of the equilibrium point, 21 to 1, which is minus 20, and 23 to 43, which is plus 20. If you want to look at it that way, they cancel each other out. Now, it seems to me that such a cancellation of common differences cannot occur further up the number line for a particular counter example. Now, I don't have a proof for that, but it seems highly logical that that would be the case. And in fact, when we look at 3x plus 1, what we really see is not a different situation, but a special case of it. And the special case is that the equilibrium is input 1, output 1. And we're ignoring the even numbers 4 and 2 associated with the trivial loop. We're just saying input 1, output 1, and we see the difference is 0. So this is a special case. We do have, greater than that, two common differences that cancel each other out. 5 to 1 is minus 4, and 7 to 11 is plus 4. And then I'm saying there are no more loops beyond this point, because there are no more cases, or there are no cases of symmetrically paired common differences. It's an asymmetric case in the case of 1. Just a special case, but a case that proves the exception, or an exception that proves the case. And so that's my reasoning behind why 3x plus 1 sequences cannot loop. Thank you.